Geo, have you ever seen the Wikipedia entry for geoid? Since you call yourself Geo, I thought you would find it funny.
I'm familiar with it. Yeah.
So have you noticed that it describes what the ocean surface would be absent tides and waves? That's it. If you just take out tides and waves, this is the elevation change of the ocean waters, static ocean waters across the world, and they show a variation in height of 180 meters in their graphic. Literally height. So if you're going sailing along the very static, slack tide, windless day, you're going to run into 180 meters of elevation, actual absolute elevation change as you sail across the oceans. Literal hills of ocean water. That's the Wikipedia definition of the geoid.
Yeah, because of the oblateness they claim.
No, it's not even oblateness. It's not the top and bottom being kind of flattened. There's like a giant, like mountainous region of water over by Australia. Very high water, absent tides and waves, of course. It's not a tsunami. It's not high tide. It's a 180-meter hill of water if there were no tides and no winds.
How does that? How the hell does that make sense?
It's funny to
Look
see
at
like
it. Just
the image without the
you gotta
water,
look-
where it's like a lumpy ball without the water. It's pretty funny looking.
yeah, but that's not claimed to be land. That's claimed to be what the water would do under ideal conditions, and the ideal conditions are just absent wind and tides. That's it. That's the
Yeah. So the water at rest. You're saying?
water at rest as hilly, more hilly
No.
than your average rolling golf course.
Yeah, I reject that. I completely reject that
You think?
concept.
I mean, come
How?
on.
How? That means gravity is affecting water differently all along that slope of the hill of water. The gravity has to be affecting it differently.
Yes. It's because gravity is, I guess, stronger or weaker or whatever, and it's creating hills and valleys of ocean water over distance. And those hills and valleys, you can see the red areas is very tall water, very high water.
Now you just changed the gravity gradient. Right? Because if you take that, say the hill, right? And we'll say, okay, gravity is weakest at the top of the hill, and that's what allowed that hill of water to form in the first place. So it gradually gets weaker in this one spot. All right, well, now keep going because it's off the center point through a ball. So just keep pushing that out into space. So that whole gradient fails. The gradient is different compared to the gradient around it. Why?
If you sail from sort of like the Indian Ocean and sail like a few hundred miles east of that, you will, if there are no waves and no tides, no wind, you will experience 180 meter, not foot, meter delta in elevation of the water. It's the dumbest thing that I have ever seen.
What would be causing that? Is it saying it's one spot because of the moon pulling the water up?
No tides, no moon involved. This is absent the moon. Look in
can't
the
wrap my head
audience
around it.
text. Here, I'll drop it in the live stream. Do you have the Wikipedia up?
No. Yeah, drop the link. I'll read it.
Pull up the Wikipedia link for geoid. It's hilarious. Geo posted the 3D version, but you have to read the actual Wikipedia because it says that's supposed to be the ocean surface. Here, I posted it in the live stream. The geoid is the shape of the ocean surface, is the shape that the ocean surface would take under the influence of gravity, including gravitational attraction of the and Earth's rotation, if other influences such as winds and tides were absent. Now keep in mind that the equator is where the highest part, the rotational part is supposed to, that's the hump, the what do they call that stupid hump at the equator? What's it called? Forgot the name of it. But where it's supposed to make that mountain in Ecuador taller than Mount Everest, right? But yet the Indian Ocean is along the equator, and it has the lowest point
Yeah,
of
I was looking at
water.
that.
And if you go just a little past like Malaysia,
Yeah, the whole Far
and you head
East is
over,
pretty much low. All through
Indian Ocean
Indonesia.
is low, and Far East is high. Red is high,
Oh,
blue is
red's
low.
high. All right. Well, I got it
Right.
backwards. Oh, what? Wow, India's way low.
Yes, but yet that's along the equator. Both of those are along the equator, where the supposed centripetal force is pushing up mountains in Ecuador to be taller than Mount Everest by 14 miles. The what's that hump called? The hump of the equator, the 14-mile hump of the equator.
Forget.
Can't think of the name of it either. Anyway, it's the dumbest thing I've seen in a while. And of course, they will defend this and say, well, yes, obviously this is true because reasons.
Equatorial bulge.
There it is, equatorial bulge. I was like, equator hump. What's the term for it? Yes, but the equatorial bulge does, for some reason, doesn't affect the Indian Ocean area of the equator. That part is deep. Look how deep that is. That's 100 meters below average sea level. According to the scale. Here, I'll post the scale. There's the scale. 80 meters above, 100 meters below. There's literally a trough of ocean surface, a valley, an ocean valley in the middle of the Indian Ocean. Maybe that's why all the garbage is collecting there. It's in a valley. Make them defend this shit.
All right, so it's saying it's theoretical analysis of measuring and calculating the effects of Earth's gravitational field. Yeah, so they're saying gravity acts different all around the Earth. And why?
And causes elevation changes of water. It causes literal 180-meter delta in elevation changes of oceans. But somehow tides and wind even that all out, so there are no elevation changes of sea level. Make that make sense. 180 meters.
Oh, so that's how they're doing it. They're taking the orbits of spacecraft and the moon and then determining the gravitational field based on that.
It's science.
Yeah, I'm looking at the geopotential
And then they're
spherical harmonic model.
Yeah. Well, that's what Daza posted. I was just like, I'll just post the geoid, and this is what the geoid is claimed to be.
Holy shit, this math is complex as hell.
And it's all based on stuff that's flying over your head.
Yeah, it's
And
exactly what it says.
them saying, this is what it would be without tides and wind. And it's like, really? How do you make that logical leap?
Triangle or like a big ass rectangle. Yeah, you could say the perimeter would affect it then, but not with a sphere.
But yet they try to claim like, oh, here's this lumpy Earth model. But then they also subsequently claim, well, here's pictures from space, and it's smoother than your average cue ball.
So, Mikey, what is the scale of those lumpy balls? Those images. The vertical scale is exaggerated by 10,000 times, right? But the deviation is actually very small.
Is it exaggerated, Daza? Is it exaggerated? Is it exaggerated by 180 meters, Daza?
So
180 meter
away,
hill,
right?
180 meter hill in height. The scale is in height, and the delta of the scale is negative 100 to positive 80, and the distance is from, say, I don't know, some part of the Indian Ocean to some part of like Asia that's just north of Australia. I don't know how far that is. Is that 1,000 miles? 180 meter delta.
Yeah.
Oh, so it's 2,000 or maybe 3,000 miles, 5,000 miles. Who cares? It's 180 meters of hill.
It's not 180 meters of hill. It's a geopotential.
So why is it? You need to correct Wiki then, Daza. You have to correct Wiki. They say it's in height.
It's the height relative to an ellipsoid, right? So the height.
Right. So correct Wiki and have a parentheses put underneath that and say relative to the ellipsoid. Is the ellipsoid a sphere, Daza?
No.
Is the ellipsoid a perfect sphere?
It's not a sphere. It's an ellipsoid.
So is the ellipsoid the oblate spheroid that has the flattened top and the flattened bottom?
Yes.
Yes.
No.
Yes. No. Yes or no.
Wait, isn't the oblique spheroid the geoid, and the ellipsoid is something else?
What about the equatorial bulge, Daza? The equatorial bulge is supposed to be around the equator. Both of these locations are around the equator, Daza. Both of them.
So
the highest high and the lowest low of your ellipsoid / oblate spheroid / geoid / whatever. The highest high and lowest low are both on the equator.
What's wrong with that?
Your top and bottom are supposed to be flattened, remember? Your oblate spheroid is supposed to be flattened at the top and bottom. They're not flattened at the top and bottom.
Okay, so you're looking at two different things here. So the ellipsoid.
Really? Let me see. Let's just look at this. Let's look at this picture right here. I want you to see the picture I'm looking at, because this is the heights right here. Are you looking? This.
Which one?
That right there. See that right there in the live stream?
Sorry, I'm looking at the wrong stream. Hang on. Okay, yeah. So this is the height deltas relative to the ellipsoid, right?
Stop saying right at the end of every sentence, because I don't agree with anything you say.
Okay. So let me explain what you're looking at in that image. That image.
Oh, please do. And correct Wiki. Please correct Wiki, because they're obviously wrong. They haven't explained this.
You let me finish then. So that image
you got to correct them, right?
That image is the geoid heights, which are relative to the ellipsoid. So the ellipsoid is the oblate spheroid that everybody loves to talk about, right? Slightly flattened
Okay,
on the
no,
top.
wait. You
And
asked me a
that's where-
question.
no, let me finish.
You asked me a question.
Let me
Daza,
finish.
you asked me a question.
Yeah, go finish.
The ellipsoid is where the oblateness comes from. It's where we get the squished, flattened top and the bulge at the equator. That
Daza, you asked
ellipsoid,
me a question. You said the
ellipsoid-
ellipsoid is the oblate spheroid. Is it true? Is the ellipsoid the oblate spheroid?
it's the one. That's the oblate spheroid we're talking about. Yes.
The ellipsoid, right?
Yeah.
So the ellipsoid, the oblate spheroid is the one that has the 14-mile equatorial bulge and has the flattened top and bottom, correct?
Yes.
Yes. And so this is the delta from the flattened top and bottom oblate spheroid.
It's the delta in geopotential. Yeah.
The delta in height, according to this.
No. It's the
No.
geopotential
So
height.
you
right?
need to reach out to Wiki and explain to them that people are very confused because you keep saying height. There's a 180-meter height difference. Obviously, it's not height. It's geopotential and needs to be in meters per second
Geopotential is
square.
height as well, right? Geopotential is height as well.
Is it? Really?
Hold on a second. Can I ask a clarifying question? Is this height, that's for Daza, is this height the height of the equipotential or the height of the surface?
It's the height of the equipotential.
Okay, thank you.
I think, yeah.
So the height of the equipotential is the what? Define height of equipotential.
O2, it is a gravitational thing. So my understanding is that gravitational potential energy is mgh, right? And these
Wait. So you asked me a question. You said right. Your understanding of gravitational potential is mgh.
Yeah. So if you've got, and in this case,
Mass,
it's the delta that's important,
times
right?
gravity times height.
The height in meters, yeah, right. So, and this
Right. From what?
is
Height
equal
from what?
heights. So
Wait. Height from what? What is
you
mgh height from?
you can do relative heights, right? And in this case,
No.
it's the relative height.
MGH is absolute. MGH has to be absolutely from something. MGH from what?
So MGH from the surface of the Earth has value, right?
Okay, so MGH from a ball, a perfect
change in
sphere?
potential energy. So in change in potential energy is fine, right?
From what shape?
The
From
change
what
in potential energy is
absolute
fine. You can measure it. You're measuring the potential energy relative to the spheroid.
So which spheroid, which ellipsoid, which geoid? Is it an absolute spheroid, an absolute geoid, or an absolute ellipsoid?
So the EGM 96 geoid that you're showing here is relative. My understanding is it's relative.
Elevation changes. Has 180 meters of elevation changes, and doesn't have an equatorial bulge.
Those changes.
Yet it accounts for rotational. It accounts for rotation. It accounts for rotation, and it accounts for gravitation. All it doesn't account for are winds and tides. So is that the idealized surface of the world, absent winds and tides?
Is an idealized geopotential surface relative to the WGS 84 spheroid. We start off with a WGS 84 spheroid, and then we measure gravitational potential relative to that spheroid.
I mean, it was clear like 5 minutes ago.
If we were to take a 1 kilogram weight and move it equidistant from the spheroid. Yeah. He said he was driving before, so maybe he's moving. I don't know.
Yeah,
I don't think he would be silent.
Finish what you were going to say.
My understanding is that
weight.
Yeah. So if you were to take a 1 pound weight and move it equal distance from the WGS 84 spheroid, it would weigh a different amount at every point because the gravitational potential is changing, even though your distance from the spheroid hasn't changed. Or if I say spheroid or ellipsoid, I'm talking about the same thing, right? WGS 84.
Really?
You know,
Really? Wait, can you hear me now?
Yeah.
Is the idealized shape, gravitational shape of equal equipotential a perfect sphere?
Yeah.
The idealized shape of equal potential would be a perfect sphere if the Earth was a point mass. Yes.
Excellent. So equipotential surface has to be a perfect sphere.
If you have a point mass.
That's irrelevant, dude. That's irrelevant to what he's asking.
What's the mass of a point? Daza, what's the mass of a point?
A point mass is a theoretical replacement for a physical mass, right? So in a gravitational field...
Wait. A point mass... Wait, explain that. Okay. A point mass is a... Stop. A point mass, you said, a point mass is a theoretical replacement for...
He's just saying the same thing you're saying, dude. He's just trying to word it a different way to get away from wherever you're going. He's trying.
Is it a perfect sphere? Is an equipotential surface, gravitationally equipotential surface, a perfect sphere or not?
if you have a perfectly symmetrical spherical mass or a
Yeah.
point mass, you will have a
whoa,
perfectly
whoa, 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 whoa,
symmetrical
whoa,
He's
whoa.
asking in real
spherical
life. He's
gravitational
asking in real
potential,
life.
right?
Like, is
Whoa, whoa, whoa,
real
whoa.
life a potential
The
surface
point,
a perfect
the
sphere?
point or
Answer
the
no.
surface? The point or the surface?
We're talking two scenarios here. Are you talking an
No. We're
idealized?
talking one scenario. We're talking an equipotential surface. We want equal potential in all directions gravitationally.
Yeah, that's
Does
the only
that
way you get the
work?
point mass. The point mass he's trying to talk about, the only way to get it is a perfect sphere. That's called the center
Exactly.
of gravity. I don't know
So if you have a
what
perfect-
he's on about. Like you're saying point mass, dude. It just means center of gravity on a sphere. It's the same thing.
Yeah.
You're saying the same exact thing.
Yeah. So if you've got a perfectly a sphere whose mass is perfectly evenly distributed,
Like a cue ball, basically. Like a cue ball, right?
Yeah.
Your
Yeah,
average
that's pretty close.
cue ball.
Will you let me
Jesus
finish
Christ, let him
for
speak.
once? So if you have a perfect sphere with perfectly distributed mass and measure the gravitational potential around it, you will get a perfect sphere of equal potential. You could replace that sphere by a point mass of the same mass, and you would get the same potential at that same sphere. That's all I'm trying to say.
It's redundant, man. I don't know why you're even bothering.
Because then we need to talk about the Earth, right? So the Earth is not a perfect sphere. It is not perfectly distributed in its mass. So
Right,
you
it
get
has a
an
bulge at the
uneven.
equator, right? It has a bulge at
Yeah.
the equator, right? And it has a centrifugal, right? That it has the rotation, right? So that's what
nothing to
you're
do with
gonna have.
gravity, though, right?
Yeah, it's gonna affect what the water does. The
Yeah, but that's
centrifugal action, right? The
yeah,
rotation.
that's why.
All right, so along this undulated fucking bulge, right? Along the equator, you would expect the same result.
That's why we use the
gravitational
ellipsoid as a reference, because
Alright, so-
the ellipsoid is already considering
alright.
the
So
effect
we
of
have
the
a
rotation.
ball.
So we
We have
don't
a
have
ball.
Or
Right.
I wish they could finish the sentence. But yeah, go ahead. Seems like you can control yourself.
I don't know. You're trying to add stuff. I don't know why you're trying to add all this pointless shit. But go ahead. If you want to get it out, man.
Just did.
All right. So if
Yep.
you take the ball and you squeeze it together, you compress it, you create your model, and you have a bulge in the middle. All right. You would expect the gravitational force to adhere to that.
What do you mean?
Right? Because now you have more mass in the center. That changing of the shape of that perfect sphere, that changing of the shape is going to change how the gravity reacts. Right? It's going to influence the gravity. Correct?
It's gonna change the direction of gravity over the surface.
No, it's going to change the
Change the
influence.
amount.
Yeah, how much gravitational pull you have, right? The
So
weight
if you're not-
on the equator versus weight at the North Pole, right? That in that sense.
But that's not due to the shape. That's due to the rotation.
Okay, so now it's not due to the shape. Just a minute ago, we just discussed the shape determines the gravitational influence, and now you're walking that back. So everything's
Didn't
based on
say
center
that.
of mass.
No, it's not.
Okay, so is it determined by the shape?
That's part of it.
Okay, so why are you saying it's not?
I didn't say it's not.
You said it doesn't have anything to. What'd you say? It doesn't have to do with the shape.
No, I said
But
the
now you're saying
difference in
part of
that. No, that difference in gravity you'd be expecting would be due to the rotation, not to the shape. If you would stop the rotation, then the gravity would be much similar to how you would get on a perfect sphere. The rotation is what changes deflects the verticals the most.
So the rotation is going to affect the gravity the most.
Yeah.
So you're saying the shape of it is kind of like a non-factor in a sense.
No, it's just like if you're in a perfect sphere, then all verticals would intersect at the center. If you're in a rotating sphere, then they would not.
Yeah, if it's perfect,
but
why
if you're
wouldn't they?
because it's rotating.
Well, yeah, I guess you get it more at the Well, you couldn't have a perfect sphere if it's rotating in that model.
Right, then you would have an ellipsoid. And an ellipsoid, the verticals don't point toward the center. Right? Because of the rotation. Yeah, on an
Where do they point?
ellipsoid. Oh, it depends.
Yeah.
It
It's because the mass
varies.
distribution changes, right, Bacon? Though because the
No,
ellipsoid.
those are two different factors. Like the
So
ellipsoid is
vertical
what
is a
you get.
gravitational thing, isn't it? Or are you talking about perpendicular to the surface vertical?
No, let him finish. Because he's saying gravity doesn't pull down.
Yeah,
He didn't say that at all. He just said
That's
it does
where he's
not. He just said it does not point to the mass
Same
center of
direction.
Earth.
Yeah,
He
then
said
it
it
doesn't
does not
pull
point-
down. That's
Right,
down,
well-
dude. That's down on a ball. Why are you
Well,
arguing?
down,
with me?
no, down is normal to the geoid.
No, down is the center. It's called inward.
No,
No, not only on a sphere.
that's only on a perfect sphere. Yeah.
Because we're talking normal to the geoid, which is and the geoid is affected by rotation, mass distribution.
Exactly.
All right, so
It's
you have
complicated.
gravity
Sure.
pulling in different directions based on the rotation. What else is going to affect the gravity?
Mass
Mass
distribution.
distribution.
The what?
Just
So can I
give
ask
you
a quick
the only
question,
two
Shugo?
factors.
If the Earth was perfectly distributed, uniformly distributed in mass, the
the
geoid would
density.
be also an ellipsoid of the same properties as the physical ellipsoid, right?
Yeah, it'd have to be the density of what's in the Earth would dictate
Yeah.
the gravity.
But the crust
this
and the
logic.
mountains. And don't forget the crust and the mountains. It's not evenly distributed. We have,
Yeah.
very deep oceans, very high mountains. Yeah, that matters.
So
Yeah,
if you started off with a perfect ellipsoid that had perfectly distributed mass, a geoid would also be a perfect ellipsoid.
Exactly.
So now gravity's
And then as we
pulling, like,
introduce mass
essentially-
distribution changes, the geoid shifts relative to the perfect ellipsoid.
Yeah, but
Exactly.
essentially it's pulling down. It might be at a slight angle or inward. It's pulling inward, and then there'd be like a slight angle, right, for the gravity. Instead of perfectly at center, it's going to be like maybe like a fraction of a degree or something.
And that's what I was going to say to Mikey before. that-
Yeah, exactly. At 45 degrees latitude, it's like 7 arc minutes.
All right, well, how do you
A tenth
end
of
up
a
with
degree.
over 100-meter difference in the height of water along the same equator?
Because
That's
it's
3,000
not,
miles, right?
it's not, and it's not a smooth there are,
Well,
there's
it's
going
not
over the Marianas Trench, going over the transatlantic ridge. Yeah, those things matter.
Yeah, but you're pulling water away from a point on the equator, and you're saying that's where it should be piling up, because that's where the majority of mass is, because it got squished.
That's through hydrostatic equilibrium.
I mean, sorry.
And that's why,
How does it
and that's
go?
why,
It would be less gravity, right?
well, yeah, and
Yeah,
and
less
that's why
gravity
the
to-
equatorial diameter is larger than the polar diameter.
All right, so there's less gravity, so you can explain the low spot that way, right? You'd be like, all right, well, it's on the equator. There's a low spot because there's less gravity, and then you look at the rest of the equator, and it's not low spots.
Well, there's a net
It's all high
effect.
spots, and there's
There's a net
overlap.
effect because across the equator you have continents and oceans. It's complicated.
Well, yeah, you're not doing a good job explaining it, so it must be pretty complicated.
You're right. You're right. In a Discord, coming up with trying to come up with summaries, yeah, details get lost. The problem with most people, in Discords, they want a simple answer, and then when you give the simple answer, they find holes in it.
What I'm
Well,
looking
that's
for-
because
is that what are you talking to me, or are you talking to somebody else? Because I didn't ask for a simple answer.
Okay. I'm talking about what I encounter.
Yeah, I
okay?
don't care about all that. I don't care, dude. I it's so fast besides the point, dude. I'm just trying to discuss a topic. I'm not trying to talk about other people on Discord.
Okay. I'm just saying simple answers. Read, then you got to fill in with details, and then the details go. Oh,
Okay, so
people think you're making up stuff.
I'm not trying to say you're making up stuff. I'm trying to wrap my head around the shit you're saying, and I'm just seeing holes in it, and some of the shit you guys are saying doesn't make sense.
So
But here's a diagram. Here's a diagram that does not include the mass distribution.
I would expect the same result between Africa to basically underneath India. I would expect that same result off the coast of South and North America.
But even the depth of the
showing
Earth is changing there. That you've got all the other, that the actual physical shape of the Earth is changing, so the density distribution will be changing. Then you have other local factors affecting the density, right? So the gravitational field is non-uniform, so the surface of the water has to be non-uniform in order to reach equilibrium.
Right, but you're talking about land masses, and you're saying the land masses affect it, and you're saying the all this stuff affects it, and then I'm asking you, okay, well, why near land masses is it the shallowest? And then you just say a bunch of words that just doesn't apply to my question. Because then I look at the Indonesia area, and that's the highest point. Well, along with above Europe, towards the North Pole.
Now, don't
So there's
confuse. But one thing to look at is make sure you're watching the signs, because in many cases it's negative, and in some places it's positive. So there's a delta above and below ellipsoid. So you can have a greater
By the way-
value, but not necessarily higher.
But Daza, I think the way maybe I misunderstood you, but the way you're trying to explain the equipotential was so you get the same weight to different locations. You're gonna the same mass on two different locations, you get different weights. And would you say the equipotential is where the weights match? How I put those match? Because I think that's incorrect.
Yes. Oh, is it? Okay.
Yeah,
If you think about it, I think it would be the other way around. For example, if you consider the ellipsoid, right? So the rotation of Earth makes it so, let's say the water would end up more at the equator than at the poles. So that lowers the poles and it makes the equator higher, right? But if you
it'd be lower.
mass,
It'd be lower at the
second, please.
equator.
Let me just finish. I'm trying to explain this to that. If you put a weight on the pole and a weight on the equator, that's the shape of the ellipsoid, but the weight's going to be heavier at the pole and lighter at the equator, right? Even though
are you including centrifugal force there in the weight, or are you just talking about the actual gravitational weight?
Gravitational weight
is
a net of centrifugal force and the mass of the Earth.
Yeah, I think that what defines the equipotential surface is where is the shape where all the normals are aligned with local gravity, not where all measurements of weight would match. I don't think they would match on over the equipotential surface. But the normal, the direction of down, would be the same as the normal of the surface at that point.
But local gravity is not impacted by the rotation of the Earth, other than that it causes the shape of the Earth to change. Right? So gravity local gravity is purely a function of the mass distribution compared to you.
It has to be affected by the rotation.
Doesn't sound right.
No, it
I
has
don't
to be
think that's
affected
right.
by the rotation, and you're going to have to.
But the gravitational attraction is
m1,
m2, and r squared, right? So that has no function on your rotational speed. But your weight, or your apparent weight, is dependent on your centrifugal rotation. that mass distribution is altered by the rotation, but the actual gravitational force is just a function of the masses.
Well, not from a reference frame on the surface of the Earth, because on a Earth fixed reference, the verticals are going to be deflected by the centrifugal force, because the centrifugal force is not aligned with the normal. Like it's on a different direction, so it changes the direction of down for a fixed observer on the surface. Like plumb lines are deflected towards the equator if you're at 45 degrees, for example. That's not part of the mass. The mass of the Earth isn't doing that.
And that's why I put the diagram up, which just addresses the centrifugal force.
So
Like
if we measure geopotential,
They don't know,